got 100 or plus. 9 got 90 to 100. Sorry, 12 got 90. 11 people got 80 to 90%. 4 people, 70 to 80. 3 people, 60 to 70. And 1 person was below. So a total of 27, 38, 42, 46 exams, of which these 38 are certainly doing A or high B work, which is excellent. I have no problem giving that percentage of the class an A or a B if you're doing that kind of work. And I noticed a lot of improvement on exams from the first time. People are much more careful in writing out their answers. So I thought I would go through some of the questions if you had any. The first problem, pretty much everyone got the orthogonal group. I took both answers. You could either take the invertible maps, B from Rn to Rn, invertible, such that preserve the inner product. That's an abstract definition of the orthogonal group, or in matrices, people said it was the A and GLNR. Those are the matrices of invertible transformations, such that A transpose times A is the identity matrix. Both of those were acceptable answers. What was not acceptable, some people said it was the elements where the determinant was plus or minus 1. That's a consequence, but you can have a matrix of determinant plus or minus 1 that doesn't satisfy this condition. And I asked, that's part one. The second part, I asked to describe the group of motions in terms of O2. That may not have been too well posed. What I meant was that the group of motions consisted of all things of the form V goes to AV plus B, where A is in the orthogonal group on 2 dimensions and B is a translation vector. Or that the group of motions consisted of elements in the orthogonal group and translations. What sometimes people told me was that O2 was the subgroup of motions preserving the origin, which is correct, and they got some partial credit for it, but it doesn't tell me what the group of motions is in terms of the orthogonal group. It just describes this as a subgroup. In any case, I apologize slightly for a slightly ill-posed question there. Part 2, this was actually quite hard. I think this may have been the hardest. Well, yeah, I think this gave people the hardest time of any of the problems on the exam, except for the extra credit problem. A simple group just means that G is simple if and only if any normal subgroup N is either equal to the identity or is the full group. Those are 2 obvious normal subgroups, and if that's all you have, that's a simple group. Now, you were supposed to show that if you had the size of G greater than n factorial and G acts on a set of size n, then it's not simple. Acts non-trivially. Sorry, that's a key word. Okay, well, the action of G on a set is the same thing as giving a homomorphism from G into the symmetry group of the set. It takes an element G and it takes it to the permutation S goes to G of S. That's what an action of a group is on a set. It's a group homomorphism. And since this set has n elements, this symmetry group is the same as the symmetric group on n letters, and this is a group of order n factorial. Now, it doesn't mean that this is an injection or anything like that. It's just a homomorphism. To every element in the group G, you get a permutation. And when you compose elements in the group, you compose permutations. Okay, but if we have a homomorphism from a group of order greater than n factorial to a group of order n factorial, it has to have a kernel. Because whatever the size of the image is in here, it has order dividing n factorial, and the order of the image times the order of the kernel has to be the order of G. So since the order of G is greater than n factorial, the kernel of rho is not equal to the identity map. Now the kernel of rho is a normal subgroup because it's the kernel of a homomorphism. It's not equal to the identity. Could it be equal to all of G? No, because we assume that G acts non-trivially on S. Namely, there's some element in G which is a non-trivial permutation, which means the kernel is not everything, because if the kernel were everything, the group would act trivially on the set S. Since G acts non-trivially, the kernel of rho is not equal to G. You have to discard both of those things. And consequently, the kernel of rho, which is always a normal subgroup of G, is a non-trivial normal subgroup, and G isn't simple. Okay, some people did it without the whole homomorphism thing, and they said, and this is just as good, they said, look, I have more than n factorial elements here. I have n factorial elements here. By the pigeonhole principle, if I have a map from this set to this set, two things in this set have to go to the same permutation. And call those things G and G prime. Then if you make the element G times G prime inverse, that goes to the trivial permutation. So there are elements that map to a trivial permutation that are not themselves trivial. That shows that if you take the subgroup of G of all things mapping to the trivial permutation, which is exactly the kernel of this homomorphism, that it's a non-trivial subgroup. Okay, that was fine too. Number 3, everyone basically got this. R is a commutative ring. An ideal is closed under plus and under multiplication from R. So if this says that A and B are in I, and R is in R, then A plus B is in I, and RA is in I. And a principal ideal A consists of all the things of the form RA, where R is in R. So all multiples of a fixed element. And a field has two ideas. So R, a field, has ideals 0 and R. Always has those two ideals. These two are distinct ideals because this contains the ideal 1. R is the principal ideal generated by 1. And they're distinct. But also, if I had any ideal, I, which is not equal to 0, and I take an element in I, which is non-zero, then if I multiply by R equal A inverse, which exists, because we're in a field, so R times A, which is A inverse times A, which is 1, is in R. So the ideal is actually all multiples of 1, which is the ideal R. So if it's non-zero, it has to be this ideal. And both ideals are principal generated by 0 and 1. So almost everyone got that one right. Okay, number 4. A conjugacy class in a group consists of all elements. So G, a group. You could say the conjugacy class of an element A consists of all elements of the form GA, G inverse, such that G is in G. The set of equivalence classes to A under the action of conjugation. And if G is finite, we find that, well, the conjugacy class of A is just always contains the element A, but it's equal to A if and only if A is in the center of G, because that would mean that all these elements are equal to A, and to say that all these elements are equal to A means that A commutes with everything in G. So a conjugacy class has a single element only if the element is in the center. So the order of G is equal to the sum of the orders of all the conjugacy classes. And we break this sum into the number of conjugacy classes that have one element and the ones that have more than one element. And the ones that have one element are just the elements of the center, so you get exactly the order of the center. That's when CA has one element plus the sum of the orders of the conjugacy classes where it has more than one. And that's all that was necessary for that problem. Okay, number 5. This was a little tricky, but most people got it. And so it was a little unclear in this one too, and I apologize to those who pointed out what you were supposed to write down. But for 5, if you have Rx, and you want to give a surjective homomorphism between this and and the ideal generated by x minus 1 to R, a homomorphism, you take a polynomial f of x, and you take it to the value of the polynomial at 1. That is a ring homomorphism, because if you add two polynomials, you add their values at 1. And if you multiply two polynomials and you evaluate at 1, you multiply the values at 1. So that's a ring homomorphism. And it has the property that h of the polynomial x minus 1 is equal to 0. So h of any multiple x minus 1 is equal to 0, because it's a homomorphism. So the ideal x minus 1 is in the kernel of h. And that means that it induces a homomorphism of this quotient ring into the ring. And it's surjective because anything can be the value of f of 1. Just take any constant polynomial to its value. So that's the proof that you have a surjective homomorphism from this to the reals, to the ring. And we have the exam? Yeah. OK, good. And then the second part is to show that this is actually an isomorphism. Namely, if f of 1 is equal to 0, then you're in the ideal x minus 1. To show h is an isomorphism, must show that when f of 1 is equal to 0, f of x is equal to x minus 1 times g of x. Namely, that the kernel of this map is exactly the principal ideal generated by x minus 1. And for this, we use the Euclidean algorithm that says we can take any polynomial f of x and write it as x minus 1 times g of x plus a constant, which is a polynomial of degree less than the degree of x minus 1. And you can do that because this is a monic polynomial. And then we find that f of 1 is equal to 0 times g of 1 plus c, which means that the value of f of 1 is c. So that if f of 1 is equal to 0, it says this c is equal to 0, which means that f of x is divisible by x minus 1. So to prove that the kernel of this ideal is precisely the polynomials generated by x minus 1, multiples of x minus 1, you have to show that this Euclidean algorithm argument works. And finally, the last problem, and the extra credit part of it, which got me some interesting answers. So 6, we have an order, g of order pq, where p is less than q. So we have a CeLO subgroup of order q, CeLO q subgroup, and all are conjugate. So it's normal, will be normal if it's unique. Well, the number of CeLO q's has the property that it divides p and it's congruent to 1 mod q. And since p is less than q, the only numbers that divide p and leave a remainder of 1 mod q is 1. So this number has to be 1. Consequently, the CeLO q subgroup is unique. Consequently, it's normal. And the extra credit problem, suppose you assume further that your prime p does not divide q minus 1. Then, in fact, the CeLO p subgroup is actually a normal subgroup in G. That's unusual, but it occurs under this because the number of CeLO p's divides q, and it's congruent to 1 mod p. That's by the CeLO theorems. On the other hand, the only numbers that divide a prime q are q and 1. Q is not congruent to 1 mod p. Because that's our hypothesis, that p does not divide q minus 1. So therefore, the only number that divides q and is congruent to 1 mod p is 1, which says that SP is normal in G. Well, how does that prove that the group is cyclic? Well, think about it. What are the possible orders of elements in a group of order PQ? You can have an element of order 1. That would be the identity. You could have an element of order p. You could have an element of order q. Or you could have an element of order pq. We have to prove that there's some elements of order pq. So let's count how many elements there are of order 1, p, and q. There's one element of order 1. How many elements are there of order q? Well, any element of order q generates a CeLo q subgroup. There's a unique CeLo q subgroup, right? So there are exactly q minus 1 elements of order q in this group. So let's put that down now. Q minus 1 elements of order q. Any element of order p generates a CeLo p subgroup. But in this case, there's a unique CeLo p subgroup. So there are p minus 1 elements of order p. So the total number of elements we've accounted for is p plus q minus 1 elements of G. But the total number of elements in G is pq. Right? Now I claim that this number is strictly less than that number. Why? Because p plus q minus 1 is certainly less than p plus q. And p plus q is certainly less than 2 times q, because q is bigger than p, right? And 2 times q is certainly less than or equal to p times q, because whatever p is, it's bigger than or equal to 2. It's a prime. And so this number is strictly less than this number, so there must be more elements of G that are not of order 1, p, or q. So there must be an element of order G of order pq, which proves it's a cyclic group. Now there's a different way of doing this, which is the way I did it in class, but I saw this, several people came up with this counting argument on the exam, which was particularly elegant. The way I did it in class, you take an element G of order p, and you take an element H of order q in our normal subgroup SQ, and those exist by the CeLo theorems. And then you consider GH G inverse, and that has to be of the form H to the A, because it has to be in SQ, and SQ is cyclic of order Q. And this A is determined mod Q, and it has the property, because if you do this p times, you have to get something that commutes with H. You find that A to the p is congruent to 1 mod Q, as G to the p is equal to the identity element. And this says that the element A has order p in the group of invertible elements mod Q. In the units of this ring. But this is a group of order q minus 1. And if p does not divide, well, it has order dividing p, I'm sorry. We just know that its p power is 1. It might itself be 1. Well, if it has order dividing p in this group, and this number is not divisible by p, then its order is 1. Because the only possible divisors of p are p and 1, and p does not divide the order of the group. Which means that A has got to, as p does not divide q minus 1, A has to be congruent to 1 mod q. It's the only thing that has p power 1 in the invertible group, which means that this number is equal to h, which means that G and H commute with each other. So you find that the element GH, which is, I don't know, K, has order PQ. That's your element that generates the cyclic group. But I found this counting argument even more elegant. So either one is perfectly good for extra credit. And a lot of people got extra credit. Looking down, it seems to me that the sizable number of people. What was the total number you gave for extra credit on this, Peter? 5 points?
Well, up to 5 points. I mean, I have 4 points for this point.
Yeah, no, but I say the maximum extra credit you could get on this problem was 5 points.
Yeah, for really
Good. Okay, but a number of people made a good stab. As I say, the one problem that gave consistent trouble was number 2, and that was because you have to think of a group action as a group homomorphism. So I hope you all enjoyed this exam a little bit more than the first exam. As I say, I think people did a lot better. If there are any questions about your performance, or you'd like to talk to me about it, please do. Go ahead.
Just a real quick question. You say so there's an element G of order PQ, and that proves that
the group is cyclic, because if you have a group of order PQ and you have an element of order PQ, then the powers of that element exhaust the group. That's what a cyclic group is. A cyclic group is a group of order n for which there exists an element of order n. That's what a cyclic group is. So the powers of that element give you the whole group. Okay? So that's what you're looking for. All you're looking for to prove that this group, it's better, you know, I said prove it's abelian. This would prove it's abelian right here. But in fact, if you're told that the group is cyclic, that's a definite way of proving it's abelian by trying to find an element of the right order. Okay? So let me just do a nice construction today, which is in section 10.6. In my opinion, it's one of the great constructions of mathematics. And it is the construction of what's called the field of fractions. And to start it off, I have to talk about a special class of rings, which we're going to focus our attention on pretty much from now on. And they're nicer rings than the average, and they're called integral domains. Okay, so we say a ring, a commutative ring, is an integral domain, or sometimes we'll just use the word domain to be short, if it has the following property. Whenever a times b is equal to 0 in R, then either a equals 0 or b is equal to 0 in R. Namely, you can't have a product which is 0 without it being a stupid product which is 0. One of the elements is 0. So, so those are called domains. So in examples of domains, R is a field, is certainly a domain. Because if we have the product a times b is equal to 0 and a is not equal to 0, then we have to prove that b is equal to 0. That's the checking of it as a domain. Well, take this as multiplied by a inverse to get b is equal to 0. Multiply both sides of this by a inverse. So if you have inverses, you certainly have this property. But there are other rings that are not fields that are domains. R is equal to z is a domain, the integers. If you multiply two non-zero integers, you get a non-zero integer. Key fact. All right? Something that isn't a domain, just to see that you don't get this all the time. R is equal to z mod 4z is not a domain. 2 is not equal to 0 mod 4, but 2 times 2 is 0 mod 4. Okay? So there you have two non-zero elements. When you multiply them, you get 0. Another example of a domain. R, polynomials over a field, is a domain. Because if you have two non-zero polynomials, of different degrees, then they have a non-zero first coefficient, right? So an is not equal to 0, so and bm is not equal to 0. Those are the first non-zero coefficients. When you multiply these two polynomials, you don't know much about it, but it certainly starts out with an, bm, x to the n plus m plus lower terms, right? And this number is non-zero because we're in a field. Okay? So that if you have two polynomials which are non-zero, their product is non-zero. More generally, this argument shows that if R is a domain, and you'll have to do this for homework, so is the ring of polynomials over R. Same argument. I didn't need that A and B were invertible, just that their product was non-zero if they were non-zero. Right? And so not only is polynomials in one variable, but so are polynomials in two variables. Because you just iterate this argument. You start with a domain. Polynomials in one variable are a domain. So polynomials over this ring in another variable are a domain. And that's polynomials over R in two variables. So there are an awful lot of domains out there. So domains have the following wonderful cancellation property, which is going to be useful for us. If A times B is equal to A times C in R, and A is not equal to 0, then B is equal to C in R. Again, that's completely false in non-domains. Yeah, so for example, 2 times 2 is equal to 0, and that's equal to 2 times 0, but 2 is not equal to 0. Okay, why is this true? Well, subtract and use the distributive law. This implies that AB minus AC is equal to 0, which means that A times B minus C is equal to 0. A is not equal to 0, so this has to be equal to 0. That's the domain property. So we can do cancellation in domains, not in arbitrary rings. And the rings we're going to study for the rest of the term are going to be rather natural generalizations of the integers. We're going to be doing number theory for the rest of the term. This is my preference because I'm a number theorist. I want to tell you what I do. By the end of this term, I'm going to be able to tell you what I worked on in the early 80s, since I've forgotten it by now, but I'll try to remember it. So we're going to be doing number theory. Number theory concerns rings that are very similar to the integers. Another example of a domain, the Gaussian integers is a domain. If you multiply two non-zero Gaussian integers, you get a non-zero Gaussian integer. Okay, now what's incredibly cool about integral domains is the following. Let's observe that if I have any ring which is a subring of a field, so here's a field, here's a subring, then R is a domain. Because if I had a product of two elements in R which was 0, then the same two product of elements in F would be 0, but F is a domain. Okay? So now you might ask, if you start with a domain, is there somehow a natural field to put it in? And that's the big proposition, big theorem. If R is a domain, there is a field, F, we can construct from R in a natural way. We'll see it called the quotient field. And an inclusion of rings R into this field. So associated to any integral domain, there's a field such that the domain is naturally included in the field. And it's the smallest thing that we can get. We'll characterize it by a property at the end. So for example, you might wonder, what are the fields associated to these domains? Well, it's somehow the smallest field you could make that contains it. So in this case, the field F is going to be the rational numbers, which certainly contains the integers, but you also can invert things in it. Here, the field is going to be what's called the Gaussian numbers, Q of I, which is all things of the form alpha plus beta I, where alpha and beta are now rational numbers. It turns out you can invert things there, even though you can't with the coefficients of integers. And here the field is sometimes denoted like this. Oops, I can't call the field. Let's call this, let's call it K of x here, where K is a field. The quotient field in this case is often denoted by K of x, and it consists of what are called the rational functions, which are quotients of polynomials f of x over g of x, where g of x is a non-zero polynomial. So it's called the field of rational functions, and these things can be inverted and multiplied, etc. Okay, yeah, Atticus.
I've been meaning to ask, when you wrote that...
This? That means included, no kernel. There's no kernel of the map. See, you could always try to map it to a field by, I mean, there are many maps of z to fields. For example, you could take the map from z to z mod 2. That would be a perfectly good map from the integers to a field by taking an integer mod 2. But it would not be an injective homomorphism. It wouldn't be 1-to-1, because it would take all even integers to 0 here. So this means that the only thing mapping to 0 is 0. So what I mean is this is an inclusion of rings. No kernel. Okay?
And are you always able, is that what you're saying? That
Yeah, we're always able to find a natural field in which R is included, called its field of fractions. So in this case, the integers turn out to be included in the rational numbers. Here, the Gaussian numbers, which are all integers plus integers times I, are included in rational numbers plus rational numbers times I. In this case, polynomials are a special case of rational functions. Okay? But when I enlarged it, I actually get inverses. Okay, so the idea is really simple, but it's deceptively simple, and it's a little tricky. The idea is just to formally invert the non-zero elements. Add elements, we'll call them 1 over a, for all a not equal to 0 in R. I mean, if we're going to have a field, then for every element in R, we have to have an inverse, right? I mean, elements in R are going to go to elements in this field. They have to have inverses. So let's try to make it in the minimal way possible. We have to have a symbol, which is 1 over a, such that a times 1 over a is equal to 1 in F. So I have the initial elements a, then I have to put new elements in my field so that they're the inverses. Now you might say, wait a minute, those might have already been there. Right? I mean, you might have taken an element which was a unit in the ring, and there wasn't already a 1 over a there. So you might have added something extra. And I'd say, you're right, that's a problem. Here's an even greater problem. Suppose we did this for the integers. So I had an element like 1/6 is in this field for R equals z. And I also had the element 1/3 in my field, because I have to invert 3 too. Okay? So since I have 1/6 in the field, I'd also have 2 times 1/6 in the field. Right? And I'd have to be able to tell somebody, some intelligent third grader who was doing this computation, that this number in the field was the same as this number in the field. Namely, these inverses that I'm throwing in arbitrarily aren't so independent from each other. Some of them are related to each other. Right? So the trick is to make a construction and then put an equivalence relation on it. And that's what I'm going to do. And it's incredibly clever if you start to think about it. So here's the construction of F from R. You start with the set of all symbols of the form A over B, where A is in R and B is not equal to 0 in R. So that's a set. Okay? On that set, I put the following equivalence relation. I say that A over B is equivalent to A prime over B prime, if and only if, well, what do you think? AB prime is equal to BA prime in R. Namely, if they look like the same fraction in the rational numbers. I mean, that's why 2/6 is equal to 1/3, right? 3 times 2 is equal to 6 times 1. This would be the symbol 2/6. This would be 1/3. They'd be equal because 3 times 2 is 6 times 1 in the ring. So I first start with a set of symbols like this. I say one symbol is equivalent to another if this is the case. Now, I have to check that that's an equivalence relation. That's not completely obvious. What is clear is that a symbol is equivalent to itself. and that it's reflexive. If A over B is equivalent to A prime over B prime, then A prime over B prime is equivalent to A over B. That's the commutativity of the ring. Okay? What you have to check is transitive. So suppose that this is equivalent, on the other hand, to A double prime over B double prime. So that would say that A prime B double prime is equal to B prime A double prime. And somehow I have to get, so I have this equivalence, I have this equivalence. I want to show that these two things are actually equivalent. Okay? So now there's a trick. You have to multiply by something, which I'm going to look up. And since I've changed notation, I'll undoubtedly get it wrong. Which one do I multiply by? Prime, and the second equality by? All right, let's take this and multiply by B double prime. So we get A, B prime, B double prime is equal to B, A prime, B double prime. And then I want to multiply this one by, any ideas? By B. Let's try by B. All right? So this becomes A prime, B, B double prime is equal to B, B prime, A double prime. All right, now let's see if we can get something out of this. So here I have B. So this number here is equal to this number here. Just, it is. It's all the same three symbols. Okay? Therefore, this number is equal to this number. Let's put that up there. On the other hand, I now use the cancellation law that both of these things are multiplied by B prime. And B prime is not equal to 0 because it was one of the denominators. So I can cancel by something that's not equal to 0. So cancel the B prime to get A B prime, A B double prime is equal to B A double prime, which is the fact that this number is equivalent to this number. Tricky, huh? So that's, again, we've already used domain right there in the cancellation to show that this is an equivalence relation. And now we define, and this is what's totally cool, F to be the set S modulo the equivalence relation, the set of equivalence classes of fractions with this relation. Now that looks good. That looks promising. I mean, that's what we really do for rational numbers, if you think about it. That, you know, if you try to describe to people why 1/3 is equal to 2/6, it's that you have a bunch of symbols, some of which are equal to some other symbols. But it doesn't solve our problem yet, because we now have to show that this has the structure of a field, which contains the domain R. So we have to put an addition and a multiplication on it such that it has inverses, et cetera, and we have to map R into it. It's not enough to say you just take a set modulo this equivalence relation. You have to say how you add and multiply. Okay, so let's add and multiply. So suppose we have A over B, and we want to add it to the symbol C over D. And then we also have to tell you what A over B times the symbol C over D is. And then we have to tell you what A over B inverse is, things like that. Okay, well, this is where you go back to 3rd grade. This is equal to AD plus BC over BD. That's by definition. We're going to check that that definition works. And this symbol is AC divided by BD, by definition. And this symbol is B over A. You can only do this if A is not equal to 0. Otherwise, you're inverting 0. Okay, now notice so far I'm okay. These are permissible symbols because B and D were non-zero, so their product is non-zero. Again, the fact that I'm in a domain. I'm only allowed to put in the denominator something that's non-zero. So this is a symbol, this is a symbol, and this is a symbol if A is not equal to 0, which is when I'm going to make an inversion. And this is a symbol that has the property that when you multiply it by C over D, you get AB over AB, which is the same thing as 1. I should say where R goes into this ring. By the way, R goes into F as you take an element A and you take it to the symbol A over 1. That's a perfectly good symbol because 1 is not equal to 0 in a domain. The 0 ring is not a domain, doesn't count. Okay, now, this isn't done yet. This is far from being done. This is just the beginning. And the reason is that you have to check that this is well defined. What do I mean it's well defined? Well, the elements of the field are not symbols. They're equivalence classes of symbols. So you have to check that if you take another symbol that's equivalent to A, if A over B is equivalent to A prime over B prime, and C over D is equivalent to C prime over D prime, then you have to check that AD plus BC over BD is itself equivalent to A prime D prime plus B prime C prime over the B prime D prime. Namely, otherwise addition isn't well defined. You could choose a different representative of your equivalence class and get a different answer. Okay, well, again, if you believe that this works, it's just a matter, I mean, how hard can this be? You're not allowed to do any calculus here. You can't differentiate everything, so it has to be pretty simple. Let's see if we can do it. B prime, D prime, and I'll let you check some of the other things. So this says that AB prime is equal to BA prime, and this says that CD prime is equal to DC prime. And what do we have to check here? Well, if you multiply this by this, we must check is AD B prime D prime plus BC B prime D prime, is that in fact equal to BD A prime D prime plus BD B prime C prime? Well, something good must happen here. Let's see what we've got here. B D prime, something must just cancel here, huh? Let's see. I think one of these is just equal to itself. So A, let's see. Help me.
Yeah, the first one. So you have an A and a B prime.
A B prime here.
And then DD prime.
And DD prime. And here I have DD prime B A prime. So this is equal to this because they're this thing times DD prime. Thank you. Same thing for the second one. Here I have a B D prime, and here is C B prime and D C prime. So this is equal to this because this is just multiplied by B D prime, something like that. Okay, good. So in fact, this fraction is equivalent to this fraction, so this addition law makes sense. It's easier to check multiplication. And so this is really the mathematical generalization of the construction of the rational numbers. And if you think about these other rings that I've made, if you take things like A plus BI and you take fractions of the form C plus DI, well, this can be written, this 1 over C plus DI could be written as C minus DI over C squared plus D squared. So you're just, so that this number would be equivalent to A plus BI times C minus DI divided by C squared plus D squared. And then consequently, here the coefficients in the numerator would all be integers, and you're just dividing by a non-zero integer. So this would be a rational number, alpha plus beta I. So anything of this form in the Gaussian integers could be turned into something of this form where alpha and beta are rational numbers. And likewise for the rational functions. I mean, if you just considered things like this where a and b were polynomials and b is non-zero, that's exactly what a rational function is. So there's no real mystery about this, but it's just such a cool construction that you can put a field structure on the set of these equivalence classes, whereas it would be extremely awkward to try to start talking about the original set itself. So this is a process in mathematics it's a generalization which was developed a great deal in the 50s and 60s in ring theory called localization. When you take Math 250, you'll spend huge amounts of time doing localization. But for all practical purposes, just the construction of the quotient field is the main example of localization. And now I'll show you what's so cool about the quotient field. and why it's the best field to construct. So this is called sometimes when you make a construction like this, you're making all kinds of what seems to you arbitrary choices, and you don't know how to characterize what you've ended up with. So here's the characterization of the quotient field, the universal property. If R to K is any inclusion, any ring inclusion into a field, that's the field K, and F is the quotient field of R, so we have a natural inclusion. This is the quotient field. Then there is a natural map of fields, a homomorphism of fields, that makes the combination of these two maps equal to that one. So that any map from a ring into a field in some sense factors through its quotient field. First you'd put it in its quotient field, then you put the quotient field in the bigger field. So for example, you could put the integers could certainly be put inside of Q of I, just as the things where the first coordinate was an integer, right? But that would factor through the inclusion of the rationals in Q of I and the map from the integers to its own quotient field. So it's sort of the smallest field that you can put R into. Yeah?
You imagine a homomorphism that would also be injective.
Yes, that would also be a homomorphism of fields is always injective because it takes, I should have said that, a homomorphism field is always injective. Because remember that a homomorphism has a kernel. A kernel is an ideal. The only ideals of a field are the field and 0. It can't be the field because the homomorphism has to take 1 to 1. So therefore the kernel has to be 0, as kernel is equal to an ideal, and the only ideals are 0 and 1. So homomorphisms of fields are always injective, so it always factors through the quotient field. So this is a nice characterization of what the quotient field is, but then you still have to prove that such a field exists, so you have to go through the fraction construction. But once you've gone through it, I'll show you that any homomorphism to a field factors through the quotient field. So let's call this homomorphism H. And I have to tell you what this homomorphism is. So let's call this thing H star or something like this, the thing that I have to construct. So definition of H star. Well, I have to tell you what H star is to an equivalence class of fractions, A over B. Right? I know what H of A is. I know what H of B is. So why don't I just define this as H of A times H of B inverse? Because I'm in a field, so whatever H of B is, it's invertible if B is non-zero. Sorry, B is not equal to 0. H of B is also not equal to 0 because it's an injective homomorphism, so it can be inverted. So H of B inverse exists in K. So if we define a new homomorphism here, then you find that the original thing factors through this. And in some sense, that shows that the quotient field is the smallest field that can contain a domain. And it's a very, very useful object. And a lot of manipulations of ring theory using domains, you feel much more comfortable to think of them as sitting inside of a field. You may not have the inverse inside the domain, but you can go to this larger object where you can find the inverse. Okay? The proof of the fact that this makes that little this is what's called a diagram that commutes. That means that this homomorphism is the composition of these two. The proof that it commutes is easy, and that's given in Artin. So I'll let you guys finish reading that part of section 10.6 and let you out a little early today. Have a wonderful vacation. When we come back, we're going to have 2 wonderful weeks of number theory. We're going to see where all these techniques of rings really get us somewhere. Okay?